Welcome to Summarize Science, where we break down the latest cosmic discoveries. Today, we're looking at a young star named T Chamaeleontis, a place where new planets are just beginning to form. Thanks to the incredible power of the James Webb Space Telescope, astronomers have detected some very peculiar signals coming from the disk of dust and gas surrounding this star. Take a look at this data from the JWST. Those prominent bumps you see, labeled ABs, are what this entire study is about. They are called aromatic infrared bands, and they are essentially the glowing fingerprints of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAHs. On Earth, you might find similar molecules in soot, smoke, or even grilled food. But in space, they play a crucial role in heating the gas in these planet-forming disks, which can dramatically affect how planets are born. The big question has been, what kind of PAHs are they, and how many are there? To find out, scientists created a sophisticated computer model, a digital twin of the T Chamaeleontis system. They tweaked the parameters of their virtual disk until its light signature perfectly matched the real observations from Webb. This model, shown here in black, lines up almost perfectly with the orange JWST data. The results from this digital detective work are fascinating. First, they confirmed that T Chamaeleontis' disk has a huge gap separating an inner and outer region, likely carved out by a young, unseen planet. More importantly, they pinpointed the characteristics of the PAHs responsible for the glow. The molecules are surprisingly small, made of 30 carbon atoms or fewer. They are also mostly neutral, meaning they don't carry an electric charge. But the biggest surprise was their sheer quantity. The study found the pH-to-dust ratio is about 16% of what we see in the general space between stars. For a single star's disk, that is a very high concentration. The team also proposed a solution to another puzzle, a strange plateau in the data around 10 micrometers. Their model suggests this can be explained by a faint population of tiny, submicron dust grains existing within the supposedly empty gap. So, what does all of this mean? Let's recap the important points. We have a high abundance of small, neutral PAHs on the surface of a disk that likely harbors a young planet. This high concentration of PAHs suggests a powerful process called photoevaporation is at play. Essentially, intense ultraviolet light from the central star is heating these PAHs and blasting gas away from the disk's surface, like a stellar wind. This process could determine how long the disk survives and how much material is left to form planets. The discovery of dust in the gap also hints that the inner disk, which might have been depleted, could be getting replenished from the outer regions. It's a dynamic and chaotic environment, and, thanks to studies like this, JWST is giving us an unprecedented front-row seat to the birth of new worlds.